Hello again, and welcome to our lecture on inverse functions. Up to now in the course, we've been talking about various kinds of functions, polynomial functions, rational functions, etc. Well, today we're going to talk about how to combine functions, and in particular, we'll talk about the composition of two functions, which will lead to the idea of an inverse function. Let me give you a taste of what an inverse function is. Suppose you have the function 5x, f of x equals 5x. That's multiply x by 5. Well, its inverse will be divide by 5. So if you start with a value of x, multiply it by 5, and then divide that answer by 5, you come back to where you started from. That's the idea of an inverse function. But before we talk about that process of doing two functions, one and then the other, let me mention some other ways you can combine functions. There are lots of ways of manipulating functions. Perhaps the simplest is addition of functions. And I'd like to illustrate it, as usual, with a very simple example. So suppose you have two functions, say f and g, and how would you add them up? Well, let's let f of x, say, be the square root function. F of x equals square root of x, and say g of x is x minus 3. Well, the sum of these two functions, f plus g evaluated at x, is nothing more than f of x plus g of x. It's exactly what you would think you would do. You just add up the two rules. So the answer would be square root of x plus x minus 3, the sum of those two functions. Okay, you can also multiply two functions. For example, using those same two, f of x equals square root of x and g of x, x minus 3, their product, f times g evaluated at x, means f of x times g of x. So the answer would be square root of x times the quantity x minus 3. So addition, subtraction, multiplication, and division of functions is pretty straightforward. Let's turn now to composition. This is evaluating one function and then afterwards evaluating a different function. And again, I'll use those same examples. F will be the square root function and g will be the function x minus 3. So what do we mean when we say f composed with g? So the composition of f with g. That means the following. It means f of g of x. In other words, first you do g of x, and you evaluate g of x. And after you have that answer, you take f of that answer. You apply f to the result of the g of x. So let's do it with this example. F of g of x means the following. It's f of, well, what was g of x? G of x was x minus 3. And what does f do to x minus 3? Well, f is the square root function. So the final answer would be the square root of x minus 3. That's the composition of f with g. Well, let's turn it around. Let's now compose g with f and see what we get. By this we mean, first you do f of x, and afterwards you apply g to that result. Okay, what was f of x? F of x was the square root function. And then we do g of that answer, g of the square root. Well, what does g do? G takes the answer and subtracts 3. So the final answer will be square root of x minus 3. Okay, we just composed f with g and g with f. What did you notice? You see any surprises here? Well, the answers are different, aren't they? And in math, we say that composition is not commutative. F composed with g in general is not equal to g composed with f. And it's even worse, or even more interesting. The domains are actually different in the two outputs. The domain of f composed with g is no longer x greater than or equal to 0, but rather x greater than or equal to 3. Okay. I'd like to do another example now of composing two functions, and you'll see something surprising coming out of this. Let's suppose f of x is the x cubed, and g of x is the cube root function. So I'm going to compose x cubed with the cube root function. So here I go. What's f of g of x? Well, g of x is the cube root, and then I take f of that cube root. Well, what does f do? F cubes things. So the cube of a cube root goes back to x. So these two functions kind of undo each other, don't they? First I took the cube root, and then I cubed, and I got back to where I started from, x. And by the way, if you do it in reverse order, you'll also get x. And this is an example of inverse functions. The cube root function and the cubing function are inverses of each other. And that basically is the theme of today's lecture, is exploring this idea of two functions composed together that kind of undo each other and come back to the original x variable. Okay, let's do the formal definition of inverse. Let f and g be two functions such that f composed with g of x equals x for all x in the domain of g, and in a similar fashion, g composed with f for all x equals x, where here again all x in the domain of f. Then g is called the inverse of f, and we denote it by f to the minus 1 power. Now this is an unfortunate notation because a lot of people think f to the minus 1 might mean 1 over f. It's an unfortunate notation. Don't blame me. It's unfortunately used all over mathematics, and we just have to live with this notation. So when you see f to the minus 1, it probably means the inverse of f, which is not 1 over f. Okay, let's talk about some of the properties of inverse functions. A function composed with its inverse, evaluated at x, will result in that same x value. They undo each other. And the inverse function actually commutes with f. F composed with f inverse is the same as f inverse composed with f. Another fact about inverse functions, if f has an inverse, then it's unique. And if g is the inverse of f, then f is the inverse of g. They're inverses of each other. And finally, here's a real important property of inverse functions. The domain and range of f, in a particular example, you'll know the domain and the range of the function f. Then the inverse has the opposite domain and range. They interchange their domains and ranges. In other words, the domain of f becomes the range of its inverse. And conversely, the range of f becomes the domain of f inverse. We'll see that in a few examples coming up. So, let's progress through studying inverses. Here's one of the first skills. How do you verify if two functions are inverses of each other? How would you know? If I give you two functions, here they are, blah, blah, are they inverses of each other? Well, what you have to do is verify the definition, that when you form the composition, you get back just x. So let me show you an example of that. Suppose f is 2x cubed minus 1, and g is the cube root of this messy little expression x plus 1 over 2. So these are two pretty complicated functions. Let's form their composition, f of g of x. So that would be f of, and now what's g of x? G of x is the cube root of x plus 1 divided by 2. Now I apply f to that globular mass inside the parentheses. It's kind of messy, isn't it? So what does f do? It's 2 times that thing cubed and then minus 1. So that cube root cubed, those undo each other, don't they? And so we're left with 2 times the quantity, x plus 1 over 2, minus 1. And now some more cancellations occur. The 2's cancel, and we're left with x plus 1 minus 1. And now the 1's cancel. Lo and behold, we're back to x. So indeed, the composition yielded x, and I'll invite you to show that the composition the other way also gives x, and we've then verified that f and g are indeed inverses of each other. Now it's interesting to look at the graphs of functions and their inverses. Here I've drawn the function f And it's a polynomial function, isn't it? It's 2x cubed minus 1. And you see it there in the graph. And then I've also drawn the graph of its inverse, which is harder to graph. But there's some interesting features about these two graphs as they compare to each other. Notice the symmetry across the line y equals x. They're mirror images of each other across that line. That's always true of inverse functions. There's this symmetry across the line y equals x. In fact, the general theorem is if a point AB lies on the graph of f, then the point BA, the flipped point, will lie on the graph of its inverse. So the graphs of f and g, or f and its inverse, are reflections across the line y equals x. Here's a picture of that reflective property. Here I've indicated a random function f and its inverse, f inverse. And the point AB is on the graph of f, and then I've indicated that the point BA would be on the graph of the inverse function. And notice the symmetry again across the line y equals x. So here's the next question you might ask yourself. Given a function, when does it have an inverse? Okay, so we know how to verify that if I give you two functions, whether or not they're inverses of each other. But here's a harder question. Here's a function. Does it have an inverse? Well, let me show you how you might tell. And again, I'll illustrate it with an example. My favorite polynomial, x squared. Does x squared have an inverse? Well, think about it for a moment. What's f of 2? That's 4, because 2 squared is 4. What's f of minus 2? That's also 4. So if f were to have an inverse, where would 4 go to? Well, 2 goes to 4, so you might say 4 would go back to 2. But wait, minus 2 also goes to 4. So you might say, well, 4 would go back to minus 2. So this cannot have an inverse because the value of 4 has two choices on where to go. And this is called, we say that the function x squared is not a one-to-one function. It does not pass what we call the horizontal line test, and hence x squared does not have an inverse as it stands. Here's a graph of x squared, our favorite polynomial, and I've indicated the 2 points 2, 4, and minus 2, 4. And the fact that it doesn't have an inverse means that a horizontal line could touch that graph more than once. And if you ever see a horizontal line touching the graph of a function more than once, you can be sure that it doesn't have an inverse. Well, let's formalize some of these ideas we just talked about. We just use the idea of what's called a one-to-one function. And this is a fairly complicated little idea that comes up all the time in calculus classes, and it's closely related to inverse functions. Here's the formal definition of a one-to-one function. We say that the function f is one-to-one if, for a and b in the domain, if you ever have f of a equal to f of b, then it must be true that a equals b. In that previous example, 2 squared equaled minus 2 squared. They both equaled 4. But 2 was not equal to minus 2. So that was not a one-to-one function. And the theorem is a function has an inverse if and only if it's one-to-one. So you have an inverse if and only if you pass that horizontal line test. Okay, good. Let's do an example of that. How about the function square root of x plus 1? Is this a one-to-one function? And in particular, will it have an inverse? Well, let's try it out. And I'm going to use the definition here of one-to-one function to show you how it's used. So what you assume is that f of a equals f of b for 2 points a and b. And then we want to show that in fact a equals b. So we're assuming that two images are the same. So assume f of a equals f of b, which means that the square root of a plus 1 equals the square root of b plus 1. Cancel the 1s, and you have square root of a equals square root of b. Now square both sides, and a equals b. Wow. Assuming that f of a equals f of b, we've concluded that a equals b. We've proven that this function is one-to-one. And I use the word proof there. It's kind of scary, isn't it? A lot of times in math we do proofs, and my students generally don't like proofs, but I often surprise them by doing a problem like this and say, congratulations, you just did a proof. Here's the graph of that function we just analyzed, square root of x plus 1. It's the square root function bumped up 1 unit. And notice that it passes the horizontal line test, doesn't it? Horizontal lines only hit it once. All right, the third question now about these inverse functions. How do you find them? You have a function. You know it has an inverse. How do you find that inverse? Well, let me show you an example. In fact, we'll take that same function we just played with, square root of x plus 1. Let's see if we can find its inverse. And here's the technique. It's kind of a straightforward technique, and some books differ a little bit in the details, but I think you'll understand how it goes. Write the function as y equals square root of x plus 1. And let's be very specific about the domain and range here. X has to be greater than or equal to 0 because we're using square roots. And y is greater than or equal to 1. Remember that graph, y started at 1 and then went off. Okay, interchange the roles of x and y. In other words, every time you see a y, put an x. Every time you see an x, put a y. So we now have the equation x equals square root of y plus 1. And solve for y. So subtract 1 from both sides, x minus 1 equals square root of y. And now square both sides, y equals x minus 1 squared. Aha. Be careful here. X minus 1 squared as it stands is not a one-to-one function. We have to think about the domain here. Well, remember, look back at the original function. What was the range of that original function? It was y bigger than or equal to 1. That means the domain of the inverse must be greater than or equal to 1. So it's really y equals x minus 1 squared on a restricted domain. The domain is x greater than or equal to 1. Kind of subtle, isn't it? The inverse of that square root of x plus 1 is the function x minus 1, quantity squared, restricted to the domain x greater than or equal to 1. Here I've drawn the two functions we just analyzed. There's the graph of f, which is that square root function bumped up 1 unit. And then I've graphed x minus 1 quantity squared, the parabola, but I've cut off half the parabola. The parabola starts down there at 1 and then goes off. And you can see that these indeed are reflections of each other in the line y equals x. Okay, let me make some comments now about functions and their inverses. The key thing is that you interchange the domain and the range when you find the inverse. The domain of the function is the range of the inverse, and conversely. Inverse functions will play a key role in this course and subsequently in calculus courses. For example, in a few lectures from now, we'll talk about the exponential function, and then we'll define the logarithmic function as the inverse of that exponential function. And later on, when we talk about trigonometry, we'll define the trigonometric functions, and then we'll define inverse trigonometric functions. Now, some good news here. If you have a calculator, the inverse functions are built in. It's really, thank you, calculator manufacturers. For example, you might notice on your calculator a key called the sine function. Well, right above it will be the inverse sine key. So we're very lucky that we'll be able to work with our inverse functions and verify our results with our calculators. All right, great. I always like to do this. Why don't you be the teacher? So here's the claim. A student comes up to you and says, teacher, my roommate claims that the inverse of the square root function is x squared. Is the roommate correct? Is the inverse of the square root function the function x squared? You take the square root and then you square it. Is that the right answer? The square root of 4 is 2, and 2 squared is 4. I'm back to where I started from. Is that right? Well, I'm afraid the roommate's wrong here. You see the problem? X squared is not invertible. It doesn't have an inverse. It's not a one-to-one function. The inverse of the square root is x squared with a restricted domain, say x bigger than or equal to 0. Then that would be the correct inverse. Here I've drawn the square root function, and I've drawn x squared, and then I've used a dotted line to delete half the domain of x squared, and now indeed they are inverses of each other as long as you've restricted that domain. Let's do an application. Suppose I have a new job. Suppose I'm working in a fast food restaurant, and they pay me $8 an hour, and they also pay me 5 cents for each hamburger that I sell during that hour. So I'm going to ask a couple of questions about my job. First of all, what's my hourly wage in terms of the number of hamburgers I sell? And then I'll ask a harder question in a moment. So let's first figure out my hourly wage in terms of the number of hamburgers. Well, I earn $8 an hour, plus I earn 5 cents for every hamburger. So I get the function 8 plus 0.05x. For instance, if I sell 0 hamburgers, I'll still get my $8. And if I sell 1 hamburger, I'll get $8 plus 0.05, 805, etc. So that would be the function that gives my wage as a function of the number of hamburgers I sell. And you could also write it as 8 plus 1/20th x. 0.05 is 1/20th. And now let's be careful. The domain here is x bigger than or equal to 0, because the number of hamburgers is greater than or equal to 0. And y, notice, is bigger than or equal to 8. That's because at worst, if I don't do a thing, I still get my $8. All right, let's ask a second question, a more interesting question. Suppose you can find the inverse function. We'll do that in a moment. And using that inverse function, can you answer the following question? For 1 hour of work, your boss pays you, or pays me, I'm the one working, pays me $10.20. How many hamburgers did I sell? If I'm paid $10.20, how many hamburgers did I sell that hour? Well, let's figure it out. Let's take our original function and find its inverse, and then answer the question. So the original function was 8 plus 1/20th x. And remember our restriction, x greater than or equal to 0, y greater than or equal to 8. Okay, x is the number of hamburgers. Now I interchange the roles of x and y, just like we did before. So x is equal to 8 plus 1/20th y. I want to solve for y. So how about if I multiply by 20 both sides? And I get 20x equals 160 plus y. And now I can solve for y. Y equals 20x minus 160. That's the inverse function. F inverse of x is 20x minus 160. All right. Who were these variables, though? Let's be careful now. X here is the amount of money I'm paid, and y is the number of hamburgers. And notice that the range previously was y greater than or equal to 8. That means the domain, x, is going to be greater than or equal to 8. And that's right, because at worst, I'm paid $8. I'm probably going to get more than that. But x is greater than or equal to 8 is the domain of this inverse function. Okay, we can now answer the question. They paid me $10.20. How many hamburgers did I sell? Well, plug in 1020 into this equation, and you get 20 times 1020 minus 160, which turns out to be 204 minus 160, or 44 hamburgers. I must have sold 44 hamburgers that hour to get the 1020 paycheck for that hour. Kind of a nice application of inverse functions, and you can imagine in real life these would be much more complicated. Another kind of application that occurs a lot, and you sort of saw it there, we interchanged variables and one was a function of the other, we went back and forth. This happens a lot, say, in temperature conversion. There are formulas that relate the temperature in Fahrenheit to the temperature in Celsius, or sometimes called centigrade. For example, you might have seen the formula F equals 9/5 C plus 32. Here C is in Celsius degrees and F is in Fahrenheit. And then you could solve for C the same way we did in the previous problem, and you discover that C is 5/9 times the quantity F minus 32. For instance, what's F of 0? Let's plug it into the formula. F of 0 would be 9/5 times 0 plus 32, or 32. In other words, 0 degrees Celsius is 32 degrees Fahrenheit. That's where water freezes. And the same is true of F of 100. F of 100 turns out to be 212 degrees Fahrenheit, the boiling point of water. So let's use these formulas for a minute. Suppose you're traveling in Europe, where they use Celsius, not Fahrenheit. And you wake up in the morning and you read the newspaper before you go outside, and it says the temperature is going to be 35 degrees Celsius. How should you dress that day? What should you put on when you go doing tourism? Well, let's figure it out. What's 35 degrees Celsius in terms of the more comfortable Fahrenheit? Well, plug it into the formula. F of 35 is 9/5 35 plus 32. And if you do those computations, you get 63 plus 32, or 95 degrees. Whoa, it's going to be hot out. I'm going to wear shorts when I do my tourism today. Okay, let's have some fun. I kind of like to give problems like this on tests. Again, they're fairly easy to grade. Not that I'm a lazy professor, but I like to give a wide variety of problems on tests. So here's a typical kind of exam question you might see. In the one column on the left, I list 5 functions, the rules for 5 functions. Let me read them to you. The first function is 3x. The second function is x plus 4. The third function is the 5th root of x. The fourth function is 1 over x, and the fifth function is x to the 4th with a restricted domain, x bigger than or equal to 0. Okay, and then in the right-hand column, I list 5 functions that are the inverses of the functions on the left. They are 1 over x, the 4th root of x over 3, x minus 4, and x to the 5th. Let's match the functions with their partners, their inverses. Let's pair them up. 3x, well, that's pretty easy, isn't it? The inverse of 3x will be x over 3. Good. How about x plus 4? Well, if you add 4 to something, how do you undo that? You take off 4, so it'll be x minus 4. How about the 5th root function? Taking the 5th root, well, the inverse, of course, is x to the 5th. Good. How about 1 over x? This one's really interesting, I think. 1 over x. Well, the inverse is itself, 1 over x. If you take the reciprocal of a number, and then you take the reciprocal of that number, you come back to the original number. That's an example of a function equal to its inverse. Kind of neat, isn't it? And the final example, x to the 4th, where x is greater than or equal to 0, of course, the inverse is the 4th root of x. Okay. What now? Next lecture, I'd like to look at a topic that seemingly, well, often seems to students superficially as a very easy topic. It's looking at inequalities. In fact, we've seen a lot of inequalities already in this course. We've talked about domains of functions like x bigger than or equal to 0. Those are examples of inequalities. X bigger than 5, x less than or equal to 7. These are all examples of inequalities. Absolute value of x bigger than 5. That said, it turns out it's not a very easy topic, I think, for students. there's often a struggle in expressing inequalities in precise mathematical language. And if you go on to a calculus course, you'll see that these ideas of inequalities occur all the time. And it's very important to be careful with the way you write inequalities. That said, in a sense, it's a review topic from algebra. And in fact, much of what I've done in these lectures so far have dealt with what a lot of people call algebra. And perhaps I've been a little confusing or going too fast, or you're a little nervous about some ideas like inverse function. That's kind of rough going. Let me recommend products from the teaching company. We're very lucky that the teaching company has courses in algebra. Professor Sellers has produced courses called Algebra 1 and Algebra 2, and it has many of the same topics that I'm talking about, but perhaps at a more comfortable level. So if this is going a little rough for you, I highly recommend these teaching company courses, Algebra 1 and Algebra 2 by James Sellers. Okay, that said, I'll see you next time when we turn to the topic of inequalities. Thanks very much.